Okay. Yeah. So I'm really glad to hope here and finished its PhD in Harvard and actually his group, but he worked on many things independently, especially I can say topological phases, SPT phases of fermions with interactions, and recently had a series of very interesting papers on measurement-induced phases or measurement preparation of topological phases using measurements, which showed that physics similar to measurement-induced transitions is actually practical in some settings. And I think today we'll talk about these things. Oh, I forgot to say now a text problem in the advertisement. So that is a postdoc in QIM. And by the way, Matt is here today and still tomorrow. So if you want to sign up, write to me. I think
Okay, thank you, Ehud, for hosting me here, and it's a great pleasure to be back at Berkeley again after 6 years. I was an undergrad here actually, and so it's nice to walk around and relive my undergrad years again. Today I'm going to be talking about how we can get long-range entanglement or topological order from finite-depth circuits and measurements, and I'll try to talk about both the theory part and how it can be applicable to current quantum devices. And so this is a series of work that was done with my advisor at Harvard, Ashwin Vishwanath, and two postdocs, Ryan Thornbrink, who is at KITP, and Ruben, who is a postdoc at Harvard. And let me just set the stage by saying that there's a complexity of quantum states. Of course, you can always start with the product state, and that's the simplest state with no entanglement. You can try to increase entanglement and get more interesting states, such as symmetry protected topological states. Importantly, these states are easily prepared in the sense that you only need to apply a finite depth circuit or adiabatic evolution by a Hamiltonian finite time to prepare states. However, perhaps the most interesting states are those that have so-called topological order, or even phases that are critical, and there are even these volume law states. And these states are harder to prepare because if people have shown that if you want to prepare them, you need, as you scale the system size, the depth that you need to prepare grows greater. And that's related to the fact that if you want to prepare such a phase, since it's in a different phase of matter, you have to tune adiabatically and you have to go through a phase transition as the gap closes. You sort of need to go slower and slower as your system size grows. But of course, these are the interesting phases. And in the past, perhaps 30 or 40 years, we have come to appreciate what could be possible in nature. And of course, this started from experimental endeavors regarding the fractional quantum Hall effect. But by now, in theory, we have sort of uncovered a large range of what could be possible, ranging from quantum spin liquids, or perhaps the most simple topological order is the Z2 gauge theory, also known as the toric code. And there are even very weird topological orders that don't even seem to fit into the paradigm of the low energy topological quantum field theory, such as fracton phases, where you can create excitations that live on fractals and they behave in a very weird way in which we don't know how to take a continuum limit properly. Of course, other than the exploration on the front of condensed matter, they're also important for quantum error correcting codes. So people in quantum information are also interested in these phases because you can potentially use them to perform topological quantum computation. Now, on the other hand, on the experimental front, we are still lagging behind a bit because only, I guess, so-called, we have discovered the fractional quantum Hall maybe 30 years ago, and we're still looking for candidates in actual materials that will realize even, for example, the simplest Z2 quantum spin liquid. But amazingly, there has been some experimental advances in the sense that let's not look just at actual quantum materials, let's just synthesize one maybe in the lab. So for example, you can have stuff interact, have atoms interact in traps, or even design superconducting qubits and have them prepare a state that might realize an interesting state. So very recently, last year, there were two groups, one from Harvard, and Michel Lupin's group. They realized that you can actually prepare a Hamiltonian whose ground state realizes a resonating valence bond solid. And so this is a candidate, this realizes a Z2 spin liquid, and they showed how this is one snapshot of it, and they just used just putting inner Rydberg atoms and having them at the right distances so that you get an interesting Hamiltonian that gives rise to this fluctuation. And also, on the other hand, there's this team by Google who use superconducting qubits to prepare a Z2 Tor code. So this is very exciting from the viewpoint of probing or exploring topological phases of matter. Of course, it raises the question: what other topological phases can these platform host, and how scalable they are in preparation? Of course, in these experiments, as I said, since it's a non-trivial topological phase, you must go through a phase transition. So when they prepare it in the experiment, what they have to do is start with the trivial phase, they tune adiabatically, and of course, if you want to go to larger systems, you need to wait longer. And of course, in the Google, they prepared using some quantum gates, but this is very specific for the system size. If they go to a larger chip in the future, they'll need more gates. So, of course, people have proven that linear depth circuits are required, and that means that as long as you increase the system size, it will take longer. So it seems that all of such preparations are not scalable. But however, there's a trick, or like a cheat. People have been talking about phases of matter using unitary equivalents. Two phases are equivalent if you can unitary connect them to the other. But of course, we can also talk about non-unitary dynamics, and one of the best examples is measurement. So it turns out that there's a cheat where you can prepare such topological ordered states quickly using measurement. And this example has been known for maybe 20 years or so. And it's related to the fact that if I want to prepare the Tor code, which has, for example, stabilizers, product of Z is on the vertex and product of X is on the plaquette, but by Z and X, I mean polymatrix here, by the way. You just need to go and prepare a short range entangled phase. There's this state called this so-called 2D cluster state, which can easily be prepared by a shallow depth circuit. Then you just need to go ahead and measure, for example, all the vertices in the X spaces. This is a non-unitary process, but doing so allows you to jump from a short range entangled phase to a long range entangled phase. And that, so if you use measurements, you can prepare Tor code or a topological phase in a finite depth circuit. So measurement gives a powerful tool to sort of overcome sort of stuff that would usually take linear depth unitarily. So this raises the question, are there any other topological phases we can prepare efficiently this way? And of course, what platforms do we currently have, for example, in this NIST devices that can implement this? So what I'm going to talk about today is going beyond known examples. So what people have known is this small box over here. If you have a stabilizer code, meaning you have a Hamiltonian consisting of terms of product of Pauli operators, of course you can go and measure these stabilizers one by one, or you can do them in parallel, and that gives you a fast way. However, I'm going to talk about how to go beyond this, and you might not even, there are states that cannot be prepared by stabilizer codes. For example, non-abelian topological orders cannot be realized as stabilizer codes, because if you only had Pauli matrices, right, they only anti-commute up to a sign. You cannot get non-abelian features which require stuff to braid up to some matrix. So you would only get a sign if you use Paulis. And the main theme I'm going to talk about today is that it turns out that anything that is related by gauging an abelian symmetry or applying Cramer's Wanne duality for an abelian symmetry can effectively be obtained easily using finite depth circuits and measurements. And once we realize this, then the possibilities just explode. And then I'm going to talk about how all of these can be realized in experiments also. So I think my computer froze, sorry. So this is an outline of my talk. So I'm going to talk about what other topological phases can or cannot be prepared efficiently this way. And first, I'm going to talk about how the known protocol of preparing the toric code or preparing these long-range entangled states by measuring cluster states can be turned into a protocol related to the Cramer's Wanne duality or gauging. I will also talk about what this can, how far we can go by going to non-abelian states. And then I'll talk about platforms that are natural to realize this, ranging from Rydberg atom arrays to quantum processors, such as in Google's chip. And so to make this more fun, I'm going to talk out of order a bit. I'm going to talk about this part first, and then I'm going to talk about the Rydberg array. Then I'm going to jump to non-abelian stuff, and then come back here. Just spice stuff a bit. So any questions before I continue? Okay, so let me just go through the known example of preparing the cluster state. So the cluster state can be prepared by using a shallow depth circuit. So let's consider two species of qubits, one blue and one red, and let's say they're in the product state in the plus space. So the way I'm writing it here is that I'm taking the red qubits to be pointing in the plus direction, while the blue qubits, instead of writing in the plus direction, I'm going to write them as a superposition, all up and all downs. And so the reason I'm doing this is that to prepare the cluster state, we need to apply the so-called control Z gate. And what that does is control Z says that if the blue spin is pointing up, you don't do anything. But if the blue spin is pointing down, you apply Z. And so let's look at, and this unitary is applied to every nearest neighbor pair. So let's see over here, suppose I have a blue spin pointing up, I do nothing. But if I have a blue spin pointing down for this pair, I'm going to apply Z to this qubit. And what Z does, it turns the plus state into the minus state. And now you see that, so for the configurations of all ups and downs for the blue spins, if I have a domain wall in the blue spins, this control Z will only be applied once. So this spin will get flipped. However, if I'm not on a domain wall, then the control Z will get applied twice, and either 0 times or 2 times. And so I get back to the plus state. So nothing happens to the red spins. This picture of preparing the cluster state can be viewed as whenever you have a domain wall for the blue spins, you decorate a charge on the domain wall, and the charge is just realized by, of course, applying a Z, because Z is charge under the Z2 symmetry, which flips all spins. And so this is the minus state here is just basically saying that's a charge. So that's a way to view the cluster state sort of in the topological manner. So now let me show you how you can actually prepare a GHZ state quickly by measuring the cluster state. So after we have the cluster state, we have a superposition of all this. Oh, I guess I should also mention that if you think in terms of stabilizers, you can also think of starting with stabilizers directly, conjugating with this circuit, and from properties of control Z, you can figure out that the stabilizers of the resulting state are given by Z x Z on every site. Now, let's say I now measure all the red spins in the X basis. That's going to pin the red spins to either plus or minus. So whatever I get for the plus spins, let's, for example, consider this stabilizer. if I pin this to be x, where x is plus minus 1, that's going to give me a stabilizer that's saying ZZ is plus or minus 1. So I'm going to get a bunch of either aligned or anti-aligned spins. And the way to see that from this wave function is that I have a fluctuation of domain walls where each domain wall has a charge attached. Now, if I measure the charges, I measure it in the x basis, that's going to pin the domain wall into a certain configuration. So for example, if the domain wall was this, the charges were in this configuration, suppose there was a charge here, then it collapses this superposition into only two possibilities. Either you had a domain wall where the spins up were on the right or left, or the spin down were on the right. Both have a domain wall here. So that's going to pin this configuration of the blue spin. And that's exactly, when you measure this, you're going to get ZZ equals plus 1, meaning there was no domain wall, or Z is minus 1, meaning you have a domain wall here. And now once you have
Can I ask one question, Matt?
Yes.
When you apply the CZs, since they're overlapping, would you consider that to be depth L or depth 1? Because they
Right. So you can do that in an alternating pattern. So you can say it's depth 2, for example, in this case.
I see. Okay, yeah. So the parallel depth is 2.
It's parallel, yeah. Thank you for the question. Right, so it's step 2 to just prepare this, and now we measure. And now using the information of the measurement outcome, you can fix this. So we know where the domain walls are. That's just the outcome of the measurement. And so, for example, if you see a domain wall here, you just need to apply X to all spins on the right, and then you just flip it. So after you fix this with your knowledge of the measurement outcome, you can then get a clean GHZ state. And now let me ignore the red spins, then you have a GHZ state. So that's a cheat. So we know that the GHZ state, in terms of phase of matter, realized as a ferromagnetic state. So if we want to prepare that, usually that would take a linear depth. But now using a finite depth and measurement, it's just using measurement, it now becomes a finite depth preparation. Let me now recast this known stuff in terms of a Kramers-Wanye duality. So I was saying we started with all states in plus. Let me ignore, and let me ignore the red size now. It can be an arbitrary state. And now I'm saying this, let's start with the blue spins in plus. These are sort of my ancillas. I apply a cluster state entangler, just a product of these control Z's operators, and then measure the red size in the X basis. For now, let me just for simplicity, let me project to the plus state everywhere. My claim is that regardless of the input state on the red, this is exactly Kramers-Wanye. And what is Kramers-Wanye? It's sending X, which is the paramagnetic term, to ZZ, the ferromagnetic term. So it's a duality between the paramagnet and the ferromagnetic phase. Why does that do that? Well, because if I push the operator X through, this control Z stuff will conjugate it and give me ZXZ. Then I act X on the plus state, this will be eigenstate plus 1. So I've managed to show that X, after I push it through, will become ZZ. And now this picture is symmetric, so I can flip it down. If we start from X on this side, it also becomes ZZ. So ZZ pushes through and becomes X. So you get a Kramers-Wanye by a finite depth circuit and a measurement. So now, well, I guess I was saying that you project, but suppose you now do a measurement. There's a possibility that you might have got the minus state. But as I said, using these information, we know where the domain walls are. The way to say this formally is that if I know there is a minus state, this is equal to the original one up to applying a Z, which flips plus to minus. Then using the Kramers-Wanye duality, we know that we can push Z back up to a string of X here. And we know that the domain walls always come in pairs, so that will just push back up to a string of X. So then based on our measurement outcome, we can fix the state and get a clean Kramers-Wanye duality. And that's why starting with the product state on the red sides will give you the GHZ state on the blue sides. So what people previously known was that doing this, but the cluster state works. We're saying this is more general. If you start with any input state that is, for example, Z2 symmetric, you'll get the Kramers-Wanye dual by doing this protocol. Yes.
But in a special case of exact state, you could correct it. Should you say you can also correct it to
anywhere in the state? Yes. Yes. So because this didn't depend on my input state at all. So this Z can be pushed through to a string of X depending on where the domain wall pairs are.
Oh, I see.
And that will give you the clean one. So as long as you're in the paramagnetic state, you don't need to be in the X equals 1. You can be anywhere in the paramagnetic state. Doing this protocol will land you somewhere in the ferromagnetic state with long range order. So that's the special case of the fixed point, right? Where you start with the product state, you end up with Z. And also in 2 dimensions, this Kramer's 1A can be thought of, well, in any dimension, but in 2 dimensions, when you gauge a paramagnetic state, you get a Z2 gauge theory, which realizes the deconfined phase is the torical. And so that's why starting with a paramagnet, measuring this cluster state gives you a deconfined Z2 gauge theory, which is a special case of the torque code. But again, starting anywhere in the paramagnetic state, you end up in the deconfined phase. Okay, so now I have 2 comments to make for 2 technical comments in case this resonates with some people. The first one is related to tensor networks or matrix product states. Turns out if I take this wave function for the cluster state, you can write it as the matrix product state, and you just flip half of the legs up. Then this turns out to be exactly Kramer's 1. So that's how the cluster state is actually secretly related to Kramer's 1, because the cluster state satisfies ZXZ equals 1 by flipping half the legs up, X goes to ZZ. So there's a very deep relation between these 2 matrix product operators. And the second one is a somewhat more gauge theory type of view. What I want to say is that the cluster state actually secretly realizes the Higgs space. And by measuring, we're saying you prepare this cluster state, you can think of preparing the cluster state is as going from the confined phase to the Higgs phase, and that those are connected. And now, what is the Higgs phase? The Higgs phase is a condensation of your charges attached with the appropriate Wilson loop. Right? So you have a Gauss law where you have a charge and your gauge fields, and the charge are fluctuating by this condensation term. So ZZ means you create 2 charges, and X means you attach a vector potential to it. Now, what does it mean to condense this? You just let this thing fluctuate. So the ground state of this 2D cluster state can be thought of as a superposition of all your E anyons in the toric code attached with appropriate strings. And now what we're basically doing by measuring the red sites, we're just picking a configuration out of this. So this is a superposition of all fluctuating charges. By measuring, we're just picking a snapshot out of it. And so we just get a snapshot where you pin the charges at some configuration. And so you get back into the deconfined phase. So going this way is condensation. You sum over all of the charge configurations. By measuring, you pick just one. So you jump from the Higgs phase back into the deconfined phase. So this is a way to think of how this is preparing. The cluster state goes from confined to Higgs, and then you sort of jump across the transition back into the deconfined phase. Okay. Any questions up until now? Yeah.
It seems like you're trading efficiency of like number of gates for losing time for sites and other stuff.
Yes, that's true. That's true. The number of sites you lose will be extensive, right?
Is there a game you can play with fraction?
Yeah, that's a good question. But I guess in terms of scalability, as long as we are able to go large in the long run, this seems to be, of course, more efficient. Yeah, but it's a good question. I haven't thought about it.
So you say it's a fine phase, radically connected to the Higgs phase, but in this case, there is also a symmetry, a global symmetry that affects the cluster state, or it's not really an SPP phase.
Oh, in this case, in this case, it's SVT phase protected by a zero form symmetry and a one form symmetry. So the one form symmetry is the same one as the one in the toric code, only one of them. And the second one is a global Z2 symmetry, where you flip all of the vertices. Yeah. So it is an SVT, but a higher form, so more exotic. Yeah. Okay. So
would you expect some surface space condition, and maybe this is between, if I go between the confined phase and
yes, yes.
confined phase, should I expect some?
Yeah, it turns out to be a surface transition. That's part of what Ruben is writing up. I'm not involved in that, but yeah, that's what they find exactly. Okay, so now let me talk about a cute way to realize this in a Rydberg platform. So what are Rydberg atoms? Basically, you just have a highly excited, a ground state and a highly excited state. You can think of it as a qubit, where 0 is the ground state and 1 is some very high excited state, and this is driven by some laser, and then the sort of effective Hamiltonian is sort of like a Ising model with long range interactions. So you have this Ising ZZ coupling where the V dies as 1 over R to the 6th. And so this gives a very good approximation of nearest neighbor interactions. And so one thing is that if you only have this Ising term, then you can actually prepare this control Z gate. So one thing is, if you evolve by the Ising Hamiltonian, you can start from a product state, and by a certain time, you'll end up in an SVT phase given by the cluster state. And that can be done by sort of momentarily breaking the symmetry. But once you get here, you'll apply some gate which realizes the cluster state. So the plan is in this protocol to start with the plus state, evolve with the innate Ising interaction of the Rydberg atom for some time, and then measure half of the sites. And so you can ask, what if you're off, this angle is off by a bit? It turns out that even though you don't arrive exactly, the correlation length is still huge. So for example, if my time for the exact time is off by 10 to the minus 3, and my correlation length is still, for example, 500,000 sites. And so in the practical Rydberg, if you ever have 500,000 sites, then you can even make a 5-meter cat state, which is something quite amusing. And you can also calculate the fidelity, because of course you have 1 over R to 6 interactions. It's not exactly an Ising gate. So you will have some imperfections, but if you compare the fidelity to the clean state, if you only had nearest neighbor, then you'd find it's still huge. So the overlap with that's measured by the overlap with the stabilizer, and that's very high. So for example, for the 2D toric code, you can do something similar, where you want to optimize making the next nearest neighbor very long, and that turns out to be best in this honeycomb geometry, and then you can find very high fidelities. You can even do this for exotic fracton phases, because right now people are starting to develop Rydberg atom arrays in 3D. And there's a recipe for you to do this. You just place Rydberg atoms in this particular manner. You evolve for some time, and then you measure the red sites in this case. And then the remaining stabilizers will realize some weird fracton order where the excitations can move freely in the Z direction, but in the XY direction, they have to move in this weird fractal geometry. So you can even do fracton phases, which people thought to be very high body interactions easily in the lab. Okay, now, yes.
You're current just ground state. So
Right.
in terms of moving, find some dynamics.
Right. So you, in terms of this type of preparation, to move stuff, you would then apply some Pauli operators so that violate some paquette or some stabilizer terms, and then you can move them. Yes.
So if you were preparing for the toric code, you know what observables to look for to see that you actually prepare the toric code.
Yes.
If you were to prepare a fracton phase, what observables
well, so for example, like what they do in the Google experiment is one way is just to measure the stabilizer. So after you prepare the state, you go ahead and measure the stabilizer and see how high the fidelity is, for example. But another way is, of course, there are certain loop operators. There's some order parameter that will vanish for this phase. For example, this Bredenhagen Mark II order parameter that people use. So you can there's something that would vanish if you had an open string versus a closed string. You can define something similar for fracton phases, but it's more complicated. Yeah. Okay. Let me move on to what else can we prepare, and of course it would be exciting to prepare non-abelian states. So let me tell you a little abstraction to them. So there are generalized cluster states known in the literature where you sort of prepare some short range entangled state. And if you project, that'll give you a Kramers-Weinert duality that gauges a G symmetry where G can be non-abelian. However, if we want to implement this projection using measurements, we run into a problem because recall that in the torical, we were basically measuring whether there is an E anion there or not, whether there's a Z2 charge here. Now, if the charge is non-abelian, you could end up measuring and find that you have a non-abelian charge there. And now, if you measure a non-abelian charge, unlike abelian anions, it's known that you cannot pair them up efficiently. Unlike the toric code where you just apply a series of Z's or X all at once, and then that just removes the string. For non-abelian anions, you have to apply it sequentially, and it's known that you have to use a linear depth to move it linearly far. So unless you use post-selection, that seems to be not a good way to prepare non-abelian states. And so the insight from using Kramers-Weinert duality is now that if you have a non-abelian symmetry, you can break it up into small abelian steps and gradually gauge the symmetry up. And so in each step, you can, after you gauge an abelian symmetry, you pair up all the charges you found, which are easy, and then go to the next step and gauge the next abelian symmetry. And then at every step, you're always pairing out abelian stuff. So if you did that all at once, it's equivalent to the thing that if you gauge the first abelian symmetry and you left the charge dangling, when you further gauge it, this might become a non-abelian anion later on. So it's important to clean that up at every state, at every step. So let me give an example to prepare S3 topological order. So S3 is a symmetry of the triangle given by rotating the triangle as a Z3, and then reflection as Z2. And it's non-abelian because these two don't commute. If you reflect, then rotate, it's equivalent to rotating the other direction. So how do we prepare a topological order with this symmetry? Well, we start with the product state. We first gauge the Z3 symmetry and we prepare a toric code. Then we apply a unitary. So right now, if we just further gauge a Z2 symmetry, we would just get Z2 times Z3 topological order. It's just gonna still be abelian. But what we have to do is we apply a unitary circuit, which turns the Z2 such that it acts and conjugates E to E squared, for example. And that can be realized as using a unitary to prepare a symmetry-enriched topological state. So now, if we have the symmetry that permutes the anions, now if we gauge that, then we would arrive at S3 topological order because the Z2 is acting in the correct way on the Z3.
So you say you're left only with Z2 after G2, and now in the second step, you gauge that.
I'm saying if I just ignore the step, the FDLU, then I end up with Z3 times Z2.
Okay.
Because Z2 doesn't act on the Z3. But now I use a circuit to turn the Z2 to act such that it charge conjugates the anions in the Z3 torus. Then after you gauge that, you'll get S3 topological order, which is not a B. And of course,
So basically, whenever you have like a normal subgroup.
yes, whenever you have a normal subgroup, you can gauge it. And right, and as long as your normal subgroup is abelian, you can pair it up.
But in those cases where it's not abelian.
Then the question is, can you further break it down into something abelian? Yeah, that's actually the next slide. But before that, let me just mention, of course, to implement the Kramers-Weinert duality, right? You would prepare some cluster state as a ZN version, for example, a measure. You would find that you have some anyons, and then you have to correct to get the clean state before you continue. So if you have left this dangling, then you would then if after you gauge the Z2, for example, E would, because of the Z2 symmetry you're gauging, E would turn into E squared. And then that now forms like a doublet under the full S3. So now that becomes a non-abelian anion. That's why it's important to get rid of it at every step. Okay, and now let me just mention it. Yeah.
Please explain it again. So you're saying these three particles, there's a abelian anion.
Yes.
Then you gauge again, that will
Right. So because of the Z2 symmetry you're gauging, E will turn into E squared. Right. Under the Z2 symmetry.
Sure.
Now when you gauge the Z2, this sort of becomes one thing. It now transforms as a doublet under the Z2. They transform into each other. So now they have two internal states there, and you can't separate them.
I see.
Because Z2 is now a gauge symmetry. So now you get a non-abelian charge, which turns out to be this irrep of S3. Turns out. Okay. So let me just flash a fun thing you can actually do in Rydberg atoms is that even though you only have two states in Rydbergs, you can actually engineer three states by putting two atoms really near each other. Then because of this Rydberg blockade, the state where two sites are both excited are not allowed. And so you have an internal three states. And we designed a protocol where you would evolve and measure, such that you get a non-abelian S3 state that can be prepared in a Rydberg atom system. And before even you gauge the second one, you can even do sort of this geometry. Of course, this can be embedded in the flat space, so you have like a disclination. But one interesting thing in this Z3 Tor code is that if you move E around, it will become E square or E bar. So this disclination realizes it traps a non-abelian defect. So even before going to like fully non-abelian, you can already explore some of these fun stuff here. Okay. So I explained this S3 as a warm-up. Now, of course, this leads to the question, what other non-abelian states can we prepare in this way? And so as you said, if the normal subgroup is non-abelian, you can't gauge it directly. So now the easiest way is to further decompose it into abelian groups. It turns out that if the most efficient way is to start with some group G, let's say that's the symmetry you want to gauge, and you compute a commutator subgroup. That'll be some normal subgroup of G, and you keep doing it until it's abelian. So you keep doing it until it's abelian. Then to go backwards, so for example, if this terminates in a single step, that's just an abelian group. If that terminates in two steps, for example, if S3, you go down to Z3, and then now trivial, that's known as a meta-abelian group, but you can have this number, as long as it's finite, then we know how to prepare it. So what you just need to do to go backwards now is that once you have the sequence, then you just gauge N1, right, to prepare, for example, in this example, N1 could be Z3 for this S3 group. And then the next one is to gauge the quotient group, which is the difference to go from N1 to N2. And that turns out in this sequence will always be abelian. And so this gives you a way to sequentially work your way back up to gauge a non-abelian symmetry. And so a fun thing is that rather than having just a map to a state preparation protocol to prepare the Tor code, you can, because you know it's gauging a symmetry, you can put any input state. In particular, it can be an SPT phase protected by G, and that can give you even more interesting phases, such as the so-called twisted quantum doubles, which are basically gauge SPT phases. So all of these can be prepared. So this is a concrete way to show that all of such phases can be prepared in finite depth and a finite number of rounded measurements.
Let's say, so this sequence is not unique for
This sequence is not unique. Well, I'm defining it such that it's unique. I'm computing the commutator subgroup. Of course, you can decompose it in different ways that is not this manner using commutator subgroups. Yeah, but it turns out it won't matter. And second, this commutator subgroup makes this length shortest, turns out. So this is the most efficient way to gauge this symmetry.
So I was thinking that maybe this is not unique, and it's following a different two procedures to go.
Oh, no, yeah, it turns out to be unique, whatever path you go. But I'm defining this as the optimal, and this turns out to be the optimal way to do it. Okay.
Wait, actually, can you define commutative subgroup forms?
Oh, it's just you have, it's a subgroup formed by G, like G, H, G inverse, H inverse for all GH. Yeah. And so this turns out to like keep going down. For certain groups, it'll terminate. Now, I'm about to say that you might think this is too powerful. Like, can we just prepare everything in the universe now? Now, it turns out that there are certain groups that are too complicated to be prepared by this. And this has a surprising connection to some mathematics known as solvability. So you might have heard that the quintic doesn't have a solution in terms of radicals. So this was something developed by Galois, and in particular, as long as the polynomial has degree greater than 5, you cannot write it. You cannot write it in terms of roots or third roots or something. There's no closed form solution for an arbitrary polynomial. This turns out to be related to the fact that the polynomial has a too large symmetry group that permutes all the roots, such that it cannot be obtained by extending stuff by abelian. And abelian is related to finding these radicals. And so similarly, there are certain groups that are too complicated to be prepared using measurement. And so the claim is that, for example, pick this alternating group, AN. So I guess I'm not comparing Galois to a soccer ball, but the soccer ball has symmetry A5, which is permuting 5 elements that an even number of permutations. And so the soccer ball has too large of a symmetry, such that if you want to prepare a gauge theory with the symmetry, you cannot obtain it by sequentially gauging abelian stuff. So it turns out that our claim is that you cannot prepare such a gauge theory with a finite number of rounds of measurement. So that's one interesting example.
I have one question here. So suppose you instead talk about inexact preparation and you ask how many rounds are required, like basically how does the fidelity per unit volume scale with a number of rounds? Do you expect that the scaling of that is different for
I think the more rounds you use, it should be, the fidelity would be lower. And one reason, actually, it's about related to the next slide I wanted to talk about. So one can ask now, what if we want to use measurement on a scarce resource, right? It would be great to minimize the number of measurement rounds you want to use, because currently in current device, you have to use mid-circuit measurement, and that's something still in development, and especially this feed-forward feature, where knowing your measurement outcome, informing what you do in the next step, people are still developing that, and not all platforms have this yet. So it'd be great to minimize this. So this is a valid question to ask practically, but also interesting theoretically, because you know that all topological phases are difficult to prepare. But now, if you ask how many rounds you need to measure, it further grades this into a hierarchy, like how many rounds I need to prepare this. Maybe some states are easier to prepare than others, right? So the last thing I want to talk about is the extreme case. So what if you only allow yourself to measure once? So you only got one shot. So you can ask, can we prepare anything interesting that's just not just stabilizer states? We know you can measure stabilizer states efficiently. If we only got one shot, can we do anything interesting, say non-abelian? And I'm gonna say, surprisingly, yes. And you can prepare a D4 topological, or D4 is the symmetry, a dihedral group is the symmetry of the square. So you have 90-degree rotations and reflection, similarly to the triangle. And now let me say that, of course, you can do it by measuring twice, as I said, this group extension method. You first, you can think of D4 as having two Z2 symmetries that are swapped by a third Z2. So that's like, you have two reflections here, and that's swapped by the diagonal reflection. So what you would do in the protocol I said previously is you prepare two toric codes, right? Then you clean up all the anions. Then you would gauge the swap symmetry, and that would realize like measuring the swap anion and you will get D4 topological order. Of course, if you did clean that up, then you would get non-abelian anions that won't be D4 topological order. However, you can actually do it in one round of measurement. And the trick is, instead of measuring E1 and E2 to prepare 2 copies of the toric, you can actually prepare it in an equivalent way. So call that E1 will become E2, and because it transforms non-trivially under symmetry, that's why it becomes a doublet. But now consider you prepare the toric code by measuring E1, E2, and M1, M2. So that's just some basis transformation, but it's equivalent. That will also prepare 2 copies of the toric code. And you can see that E1 and E1, E2 transforms as a singlet under the swap symmetry, right? It's invariant. And so you don't need to correct this. And after you gauge the swap symmetry, it'll still be abelian. And so you can delay the measurement and actually measure all 3 of them at the same time. And that will give you D4 topological order. So that's the amazing part. You can measure E1, E2, M1, and 2, and the swap symmetry all at once. So you prepare some complicated state, measure once, and you get D4 topological order. So, yes.
So when you say measure swap symmetry, you measure the charge on the swap? Or?
Yes, measure the charge of the swap symmetry. Yes.
Basically, parity measure.
Right. So that what I specifically mean is like in the toric code, right? You measure the 4 body Z. That's like a Gauss law for your charge. So I'm saying there's an equivalent Gauss law for your swap symmetry. Measure that operator, and that will inform you whether there was a swap charge there.
Just this model was that like how complex is that operator? Is that volume maximum?
Right. That's what I'm going to talk about next. So here is your cookbook to prepare D4 topological order. And you can just go through these steps. It only requires 2 body interactions, which are control Z gates and single site gates. And at the end of the day, you measure certain qubits, and then whatever is left will realize D4. So let me walk you through that. So first of all, I'm going to create a certain cluster state known as a dice lattice cluster state. And it's known that if you measure, this is the dashed lines, which connects all vertices to plaquettes on the honeycomb lattice. It's known that if I measure that, I'll get a color code topological order. And it's known that this is equivalent to 2 copies of toric code. Now, what I next do is I do a single site rotation that turns out to be some derotation and some Hadamard. And basically it turns the so-called swap symmetry into a prod X symmetry. Then once I have this symmetry, now I know how to gauge it. I just do this cluster state entangler to go from the vertices to the edges, and then I gauge the symmetry. And what I do that by measurements, but I can delay all the measurements. So if I start measuring here first, I would have prepared color code, but it's not necessary. Oops, sorry. It commutes with everything else, so I can measure everything at the end. And that's basically how you would prepare this state. So you start from the product state, you prepare some complicated state using only 1 or 2 body gates. Afterwards, measuring gives you plus. Okay. Okay. I think I'm almost out of time, so let me rush a bit. Let me just point out that you can do this on a Google quantum processor. We found a nice way to embed this, and you only need an extra few steps, with, 2 more steps, which is requiring some swapping. So just 2 more layers of swap. You can embed everything into this square lattice connectivity where you can only apply 2 body gates on the square lattice. And so this gives a way to, even if Google has a larger chip, it'll still take the same depth, like depth 11 or something. So it's very shallow. Let me comment on what else you can prepare in one shot. This actually generalizes to so-called non-abelian phases that admit a Lagrangian subgroup. What that is what you only need abelian bosons, or your anyons have to be bosons, and they braid trivially with each other. And the only other condition is that they have to braid, anything else braids non-trivially with the set. So you can think of it as, let us start with this topological order. I can condense all my anyons in that set. That'll confine everything, all the other anyons, not in the set because it's braid non-trivially. And I'll end up in some short range entangled state, which is protected by the symmetry group A. Then we know that this SVT phase can be prepared efficiently from a product state because it's short range entangled. And now you just need to gauge to go back. So you're measuring abelian anyons, but at the end of the day, you can still prepare non-abelian symmetry for any anyon theory that satisfies this. I just want to show you, I just want to flash you, I'm not going to explain this, just there's a class of topological orders for some group G. If G is an extension of the central extension of abelian group by abelian group, like D4 or the quaternion, they can all be prepared. And here's a protocol. You don't need to let it sink in, but I'm just saying that it exists and you can prepare exactly the quantum double state. So in summary, yes.
So it needs to be a subgroup, not sub-object.
Yeah, by group, I'm secretly saying it has to be abelian.
I think you need to have like an edge that is a gap edge that consists only of the abelian.
Yes. Okay. So to summarize, I've said that certain like non-abelian topological orders such as D4 can be prepared efficiently using only one round of measurement. Here, the dotted lines tells you how many rounds you need to prepare. Where actually for S3, we believe you still need 2 rounds to prepare it. So it gives you a hierarchy of states, how many rounds you need to prepare it. And moreover, there are certain states such as the symmetry group A5 where you cannot prepare efficiently. And some other examples are Fibonacci anyons, for example. There's a similar argument that in some sense it's non-solvable, but that goes beyond the notion of group. And so other fun facts that I didn't have to have a chance to tell you about, you can, for example, show that not just measuring fixed point XTT phases, anywhere in the phase should give you long range entanglement in general. You can generalize Kramer's one-edge to Jordan-Wigner. If you have fermions, you're just basically like measuring a Gauss law for a fermion. And you can even prepare chiral phases such as Ising anyons. And so the trick is, well, you have measurement, right? Prepare the double Ising model. Turns out you can do that by gauging abelian stuff. Then now you have 2 copies, just measure one, the lower layer, right? And now you have something chiral that usually cannot be prepared. And then last thing that I didn't have to talk about is some work with the same team, but also Guoyi Zhu and Simon Krebs from University of Cologne. We studied how stable it is to prepare if you miss the preparation by a bit. For example, using this Ising interaction, if you miss a bit, turns out in the 2D toroid code, you would immediately go away. But for the 2D GHZ state or 3D state, that turns out to be stable, and then there's a transition. And it's somehow related to the persistence of these phases to finite temperature. So please ask me after the talk if you're interested about this. And as an outlook, it would be interesting to prepare non-abelian states as an experiment, of course, that's very exciting. One thing I still want to think about is after you prepare such a state, how do you do universal quantum computation, or how do you do active error correction once you prepare that state? And the second is there seems to be a theme emerging that gauging and measurements are intimately related. Also, condensation can even be thought of as gauging if you think about it as gauging a higher form symmetry. So there should be some connection between that. And recently I learned that they're in fact relevant for these dynamical flow K codes people have been constructing. So I'd like to learn more about that. And also maybe a very purely theoretical mathematical point of view. We have a new class, there's a new sort of equivalence class of phases, right? What phase can be prepared from A and B if you use measurement? That's not the same class anymore. So what mathematics capture that? So people know there's some category theory description of phases of matter. What type of math captures this equivalence class? Okay, and so thank you. And there's Imu made a sign-up sheet for me, so I made a QR code. So in case anyone wants to chat, just take a picture.
So this point on measurement equivalent phases. So is it really correct to think of these as equivalence classes? It's not. I would think it's not reflexive. For instance, the products taken from any arbitrary.
Right. So in the definition, you say you have to be able to go both ways. So
Okay,
yeah.
sure.
So that's how you get rid of the non-symmetric.
So I think there also exists non-poly versions of like stabilization codes that realize some of these non-abelian topological orders. But the issue there of just measuring stabilizers that you don't have an isolated bearing on resultant charges.
Well, so in fact, the states we prepare here can be realized as well, I wouldn't call them non-poly, they're just non-stabilizers. They use something outside of the poly group. It'd be in the Clifford group.
But everything would still commute, like all of the.
Everything still commutes, so it's like a commuting projector Hamiltonian, but it's not obvious how you would go and measure that.
I see.
Because they only commute up to in a low energy subspace of other projectors, for example. That's what makes it hard.
Are there states that are based on non-solvable groups, so the ones that are hard to prepare? Does that mean that they have some additional thing that they can do that you can't do? Like,
Right.
Correlated with the recursive computer, but not.
Right, that's what we noticed as well. And so Kitaev pointed out, well, Kitaev remarked without proof in his paper that if the group is non-solvable, then it has a universal gate set. And so there seems to be some hierarchy of stuffs that are hard or are more powerful, for example. And also there's a relation to this nilpotent thing that I flashed earlier, that if a group is non-nilpotent, there was some paper that showed that you can still get a universal gate set if you are allowed and still as in measurements. So these are easiest to prepare, but also people don't seem to know a way to get a universal gate set out of these spaces. So they're simple ones.
Two questions. One very basic on your code preparation. If I understand correctly, as a basic preparation scheme, you encoded a very specific qubit to your code space.
Yes.
And you control what qubit you encoded.
Yeah, because you know all the measurement outcomes, you can basically pair them. There, of course, once you have the anyons, there are two ways to pair them up. But based on, because you know exactly what state you prepared, you can choose which way to pair that up so that you end up at specific logics.
That would be linear, right?
No, because you can apply all of them at once, right? Just apply all the z's in one go.
I see.
That's why it's easier for abelian, but not for non-abelian.
I see. So yeah, my kind of follow-up question is, if you wanted to prepare a non-abelian state, not in the ground state, but maybe with a prescribed set of non-abelian ions,
Right.
maybe even encode information into that space. Is that possible, or that would be again that would be at least linear?
Oh, so you can actually.
Even in my
So there's a paper by Bravi that showed that you use measurements, you can actually move them efficiently. And I believe it's related to the fact that, okay, you can probably sort of ungauge so that it's simpler and then gauge back up so that you have this string. So it's equivalent to not fixing the measurement outcome, right? So instead of this is used for the measurement, but you just leave two of them there and then
that's what I thought.
so you can sort of go back and then.
They're there, but how do you encode the information in them? Is that
Right, so they will be initialized in a particular one where they're in the singlet.
okay?
But then, yeah, that's how they initialize. But then, of course, you have to do grading if you want to do more stuff, right? It's the way to start.
Sir, a technical question. So how to prepare S5? You said S5 can be prepared.
Oh, in that box, I'm saying S5 is in the same class as S5 is in the same class as A5. So suppose you had a way to prepare A5, then it's in the same class. You can gauge a Z2 symmetry basically to get a S5. So these are in the same classes. Yeah.
So you're talking about some category theory object. What do you mean by like, in what sense would you want something more than like model theory?
Oh, it sort of collapses these modular tensor categories into an equivalence class. So there's a sort of a coarser data there where all these solvable groups are considered trivial, and then there are other stuff. So what is it collapse? So for example, I can tell you for groups, I can show that for every finite group, you can collapse it down to a simple, a simple centerless group. So it's a group that has only non-abelian anyons. So all the charges and fluxes are non-abelian. So for example, A5 is one example of that. A5 doesn't have any abelian anyons, and that's sort of why there's an obstruction. If you want to measure somehow and enter A5, right, there are no abelian anyons to start with. So it's sort of, it's reducing the problem to like find something that only has non-abelian stuff. Then there should be an abstraction to compare that.
Isn't that the whole point of the field section?
The whole point of what, sorry?
Field extensions in the left here. Is this making this hierarchy?
Yes, yes. So that's for groups, but now, but now you can ask the same thing for Fibonacci, which is on a group. And so now you need some category. Yeah, so there are some notions of solvable categories that people have defined, but yeah, it's still not clear to me whether that matches the thing we have for this equivalence or not.
If we consider overall complexity of the procedure, including the classical part, is it going to be, is the procedure reducing the complexity from OL to 1, or is it still?
So you're saying classical what again?
Yeah, so you make a measurement.
Yes.
And then you do some kind of post-processing to figure out which kind of gates that line
Yes.
you want to either cancel the anyons or cancel
Yes.
the angles.
Yes.
For the case of the GHD state,
Yeah.
I think that procedure is still linear in the system size, right?
Well, you can do them all at once, but
to figure out which gates that apply, still need to be.
it'll be linear classical processing. Yes. So there's also something I swept under the rug is you need to know that you need to propagate that classical information. So you're still limited by the speed of light, so to say. So you don't have the usual light cone in the quantum circuit, but it's now you increase it to the actual speed of light. So you need to, so it's still bounded by that, but okay, for experimental purposes, you probably say that's infinite.
But in the case of toric code, can there be like one decoder, like because now we are looking at something like topological quantum memory and the voice.
Well, if you keep everything classical, you can just pair up stuff locally. So there's probably a sort of RG decoder that probably works because you don't need to end up in the exact state where the logic was +1, right? You can just group stuff up and with that knowledge, just continue and process classically without having to do it in the actual state.
I see. Okay, thanks.
There are no more questions at the same time.
Thank you.